So I'd like to go through these last few slides that we went through in class because it was a bit rushed. I'll take it a little bit more slowly. You're welcome to skip ahead if you like. And then we have a couple of slides at the very end that I did not get to that I wanted to cover. Okay, so let's go back and consider the effect of excess charge placed on a conductor. We had talked previously, earlier in the lecture, about putting a neutral metal sphere in an electric field, and we saw that there was separation of charges, and as a result of that, we got zero electric field inside the conductor. And that was a general finding. The field inside a conductor is always going to be zero, the net electric field. So now let's move on from a neutral conductor to a conductor that has some extra negative charges, say, is thrown on there. Could be positive charges, it could be negative charges, right? But it has excess charge, so it's no longer neutral. Well, on a conducting material, charges are free to move throughout the conductor. That's the definition of a conductor, right? Like a metal. So since the charges can move, when we put extra charges on there, we have to ask, since they don't just stay where we put them, how are these excess charges going to redistribute themselves? Right. And the answer is that turns out all the excess charge that you put on a conducting material, we'll say, for an example, a conducting sphere made of metal, they will all go to the surface. So we'll do this for a sphere, but it's true for any conducting volume. Now there's two ways that we can justify this statement, that all the excess charge goes to the surface of the conductor. One is with this logical argument, right? You might ask, why wouldn't the charge just evenly distribute itself throughout the volume, right? I mean, if it could move anywhere in the volume, wouldn't it try and maximize its distance from everybody by distributing itself as evenly as possible throughout that entire sphere, right? The reason it doesn't do that is it's actually an unstable situation. What we mean by this is, let's imagine that you did do this. That, let's take a little cross section through the sphere. So I'm here where I've kind of cut out a wedge so you can see that the inside of the sphere has no charges. Let's cut right through the middle of the sphere. Right, so I'm looking in the middle of the sphere, and let's pretend this is not what happens. Let's pretend that the charges are distributed evenly throughout the sphere. Let's see what would happen if that were the case. Let's look at, say, this charge over here towards the left, highlighted in purple. Right, if it's a little bit off center, and it's over to the left, and we look at what this charge sees, right? He sees that there are now more charges over to the right than there are to the left, right? And as a result of that, because this charge feels repulsion from every other positive charge around it, right? Then since there's more charges to the right pushing on it than there are to the left, it's going to get pushed this way overall, right? So it started off to the left of center. It's going to get pushed even further to the left of center. Another way you can see this is if you imagine these are the charges that are to the left of it. These are the ones that are trying to push it to the right. Right? Well, I could balance that force perfectly with a equally sized and shaped volume to the right of it, which would be this thing, right? So if it were just these charges, this guy would be imbalanced, at least in the left-right direction. Right? But it's not just these charges. To the right, there's also all these charges in this kind of crescent moon shape that's still gray, right? And these charges also push it to the left. So whereas this section balances this section, this is unbalanced, and this charge will end up getting pushed to the left. Well, if it gets pushed even further to the left, then there's even fewer charges to the left of it, right? Which would get balanced by an even smaller wedge, which would leave even more of a large crescent moon, pushing it even further to the left, so it would get pushed even further to the left. Eventually, it get pushed all the way to the left edge of this thing, trying to escape as far as, now everything's to the left of it. It wants to move outward as much as possible, but it can't leave the surface conductor, so it's just stuck there at the surface conductor. Right, now I could have drawn this at any orientation, right? I could have picked a charge up here, right? And then drawn all these shapes, and the result would have been that it would have been pushed out this way until it hits this side of the conductor. I could have done it over here for this charge. I could have just rotated it so that this charge now looks over like it's over here. Well, I would draw my, blue sliver up here. I would draw my red counterbalancing sliver here, and I would leave all these charges down here, right, which would push it up in this direction. So you see, no matter where you put the charge in the conductor, it will end up being pushed radially outward, right, until it can't go any further. And the end result of that is all the charges are pressed up against the edge of the conductor. Okay. So the other argument we can make to prove that all the excess charges on a conductor will very quickly move to the surface of the conductor and end up distributing itself there in the steady state is Gauss's law argument, right? We know from the previous set of slides that the electric field inside a conductor is zero. So if we draw a Gaussian surface, this imaginary surface, this is like a spherical closed surface, right? I can't really draw a dashed sphere very easily. And we make that sphere completely contained inside the conductor. Well, then the E field that crosses that surface must be zero everywhere, right? Because the E field everywhere inside the conductor is zero. So when we sum up all the E fields crossing the surface to figure out the flux, right? The flux has to be zero, right? Because if the E field is zero everywhere, then you sum it up across all areas to get the flux, and the flux must be zero. Well, Gauss's law states that the flux through any surface is equal to the charge enclosed by that surface, right? Well, we just said that I can draw this Gaussian surface inside the conductor. It'll contain no electric fields, right? Because the electric field everywhere in here is zero. So the flux through the surface is zero. But if the flux is zero by Gauss's law, the charge enclosed must be zero, right? So this surface must have no charge enclosed. But I can make the surface, I drew it small, but I can make the surface bigger and bigger and bigger. And the E field everywhere inside the conductor is zero, so the flux is zero. So the charge enclosed by this increasingly large Gaussian surface is zero, right? I could do that all the way up to just under the edge, the skin of this conductor, the outer surface of this conductor, and all the results would hold true, right? So that would imply that no matter how big I make this thing, all the way up to the size of the conductor itself, there are no net charges inside, which means all this excess charge that's on the conductor has to be right at the surface. It has to be sitting outside on the outer surface of the conductor. So in summary, for a conducting sphere, all the excess charges that you place on it will quickly redistribute themselves so that they are all on the outer surface of the conductor. That allows you to put a Gaussian surface inside the conductor and have no charge be contained, which has to be the case because we know that there's no E field in here, which was our other result, right? That the E field inside a conductor has to be zero. By comparison, if we had a styrofoam ball, something that's insulating, right? And I somehow were able to create excess charge and put it in and distribute it throughout the sphere, then those excess charges would be able to stay there, right? Because charges can't migrate through an insulator. So we could actually stick them there and they would stay there. That would mean that a Gaussian surface that you place inside an insulator could actually contain net charge, right? Which implies that the electric field inside an insulator can actually be non-zero, okay? So I believe there will be a homework problem where you're asked to calculate something for an insulating sphere. And the way you can do that is to make this Gaussian surface and figure out how much charge is enclosed, and that will let you figure out the E field. And how much charge is enclosed, if we assume that, and I think the problem assumes that the distribution of the the excess charges is uniform, then if you take a sphere of this size, then you can figure out what its volume is compared to a sphere of the entire size of the sphere, right? Let's say that this is 1 meter and the sphere was 3 meters. Well, the volume of a sphere scales as r cubed, right? And so you can figure out how much volume is contained here versus contained in the entire thing, and the amount of charge enclosed would just be that ratio. Let's now consider what happens when the conductor is asymmetrically shaped and has maybe some sharp edges. Right. So let me preface this by saying that uh, I don't think we have any homework problems on conductors with sharp edges. I'm not going to test you on any of the mechanisms that we're going to cover here. The only thing you might need to know at any point is the end result. So if you have a conductor that has a sharp point, then at that point there will be a tendency for any excess charge to accumulate or any induced charge to accumulate, and as a result, the electric fields will be strongest there. That's the only thing you need to know. And if you aren't interested in why that happens or the mechanisms, you can skip the rest of these slides. But for those of you who are interested, here we go. Let's now consider something that's less symmetric, right? Something that maybe has a sharp edge, right? So we'll take our sphere and we'll kind of stretch it on one side so that it has a sharper edge on one side than it does on the other. So we're going to put some excess charge. We know that any net charge or any excess charge on the conductor will quickly move to the surface, right? And after that, they're only allowed to move along the surface because we know that if they move inward, that any charge placed inside the conductor will end up getting pushed right back out to up to the surface. So the redistribution is effectively going to only be along the surface. So where do they distribute themselves along the surface? Well, in a sphere, everything's perfectly symmetric. It has to be symmetrically, right? But what happens if it's asymmetric? What if one side looks different than the other? Well, we know that because all the excess charges are the same sign, by definition, right here, positive charges, these charges are going to repel each other. They're going to want to try and get far away from each other, right? So what we've drawn here is imagine that these are neighboring charges. We've obviously exaggerated their separation to make the illustration easier. But let's say that this charge feels the force on this charge, right? Remember that the Coulomb's force acts along the centers or along the line that connects the centers of the two charges. So these are vertically separated. So the net force on these guys is outward, right? The electric force, I'm sorry, is upward. So that would also be the case over here. But what we know that these guys are constrained to move along the surface, right? They're not going to jump off of the conductor. We're not going to work in that regime. And they can't move into the conductor. So they can only move along the surface in the tangential direction, right? So tangential meaning, again, parallel to the surface. The tangential component will actually be able to cause the charge to move because that's the only way it can redistribute itself. We just said that that's what happens. It distributes itself along the outer surface. But notice that the tangential component of that force is actually weaker, right, when you have sharper edges. Over here, so what we do is we place that clipboard, down here like this. We kind of lay it down so it touches at this point, and we say, well, what component of that force, so we have this plane that's along here, and we have a force that's going like this, right? So we want to know what component of that force is along the plane, right? Along the surface, right? Local surface right here. So we would project this down and see how big it is on this plane, and it's that big, right? On the other hand, over here, because of the sharpness of this, tangential plane actually looks like this, right? It's more shallow, right? If you take it to an extreme, let's say that we had something that was really pointed like this, and you can see that the tangential component, the plane, would almost be horizontal. The force between them is still vertical here, right, as drawn, right? So on a clipboard that's laid like this, right, parallel to the surface at this point, this force would have a component that is much smaller compared to this one. The net result of this analysis is that the effective force moving these guys apart, right, moving them away from each other along the surface, is smaller in regions where there's sharp edges than when you have a nice smooth surface over here. The net result of that is that since the force that can cause them to move away from each other along the surface is weaker, they will be more tightly packed together. So you'll have more positive charges packed together near a sharp edge than you will when you have a smooth contour like this, more rounded contour. If you have excess charges, like we drew here, right, then the excess charges will be more concentrated at the peak. Similarly, if you have a neutral conductor that's irregularly shaped and you place it inside of an electric field, that electric field will induce a charge separation just like we did with the sphere, but now those charges will also redistribute themselves on the surface, and the redistribution will be more widely spaced on this rounder edge than it will be at this very sharp corner edge, right? So again, you'll have a concentration of charges at the corner, right? And that will cause the electric fields to be stronger there as well. All right, so now let's look at some consequences of this effect of charges accumulating in sharp corners, right? One place that this shows up is in a microwave oven, right? So microwaves heat food using electromagnetic field that is used to basically rotate and oscillate the molecules in the food to warm it up, right? Like the water molecules. So if you place a metal object with sharp corners, like a fork, inside the microwave, then the electric fields inside the microwave will cause the charges to concentrate and the electric fields to concentrate at the sharp corners of the fork, like the tines of the fork. The local electric field strength can get so high that it can actually cause air to break down and become conducting. Right? So this is phenomenon of dielectric breakdown is something we will cover when we talk about capacitors in just a couple of chapters. But for now, I think it's kind of interesting to preview this with a demonstration that I did show at the end of the class, but now we will show it again if you're interested. Right? So in this demo video, there is a CD that I'm going to place inside a microwave. The CD has all these little divots in it that encode the data, right? So there's ones and zeros that are encoded as little corners, right? Little divots and hills. And then that whole thing is coated with a reflective layer of aluminum. So effectively, you've got these conductors, this conductor with millions upon millions upon millions of these little sharp corners, right? So at every one of these sharp corners, you're going to get an accumulation of charges, right? And you're going to get very large electric fields, and they can cause air to break down, meaning a spark will occur between them. And let's see what happens. All right, so we're going to do a little demonstration of how electric fields concentrate at edges, sharp edges. So we'll put a standard CD in a microwave. This is a rewritable CD or a writable CD. We're going to have our fire extinguisher nearby because this is a fire hazard, so do not try this at home. And let's hit start. And it really stinks up your microwave and maybe puts a burn on your wife's favorite dish towel. So now I'm in trouble. And here's what we have as a final result.